Hello to all of you and welcome back to my SB2 channel. This video is all about the gas mixtures and partial pressures. We're going to be looking at how we can do the calculations for mole fraction as well, and I also have a quick practice for you at the end. Okay, so let's talk about gas mixtures and partial pressures, starting by a mixture of a gas. If you think about all the lectures that we have so far in this chapter, we were only interested in one single gas, one pure gas. This lecture is different. Now we're talking about a mixture of different gases. You can imagine something like air would be a good example, right? Now, John Dalton discovered an important principle, which is pretty easy, kind of a straightforward and very understandable. He believes that the total pressure of a gas mixture is always going to be equal to the sum of all the pressures that we have for each of these gas if they were alone. We just need to sum them up and that will be equal to our total pressure. Okay, cool. So more about that on the next page. Follow me on the next page, please. Okay, so looking at this very simple picture, as you can see, we have three different containers. For gas A, gas B, and gas C. And what happened here is we are combining all three of them to make one mixture. And that's the one that you see at the bottom of the slide. So we can go by partial pressure of each of these gas, which is going to be the pressure of one component, just one gas, in a mixture that we have, and that is known as your partial pressure, right? Now, according to this Dalton's law, as we said, the total pressure is going to be the sum of all of these individual pressures. We just need to add them up, right? Now, if you think about that, this means that each gas behaves independently. We're not going to have any chemical reactivity between these gases. There's no chemical reactions. We just put them all together so they can behave independently, right? It seems that there's no other people around them, right? And that's what all I need to do is I need to sum all of these pressures and that would give me my total pressure. Okay, I hope that makes sense. Okay, now I'm going to take you to the next step. We're going to be using ideal gas law, as you remember from our previous lectures. And each of these gas is going to obey the ideal gas law because we're going to treat them all ideally. So I can write down the pressure for each of them using ideal gas law. That will be nRT over V. For each of them, we have to plug in the N for that specific gas. Okay. Now they all are in the same mixture, right? And therefore they're going to have the same volume, same container. They also are going to have the same temperature, right? So if the volume and the temperature are constant, then you can add them up and that will be equal to the moles, right? The total moles times by the RT divided by volume. So as simple as just using the ideal gas law, plugging the total number of moles of the gas, right? And then we can calculate the total pressure. So one way was adding all the partial pressures. That's one way that we can get the total pressure. This is another way that we can calculate the total pressure. Okay, I hope that makes sense. Okay, now let's talk about mole fraction. So I want you to think about mole fraction as one way that we can define concentration, right? So the concentration for the gases can be calculated using mole fraction, okay? So the mole fraction of a gas in a mixture is going to be equal to the number of moles of that gas, which goes by Ni, divided by the total moles of the gas that we have. For example, if you have nitrogen gas in the air, the number of moles of the N is going to be the Ni, right? And then you divide that by the total moles of that gases that we have in our mixture, and that would give us the mole fraction, okay? Now, this is going to be always like dimensionless. We don't have any unit for that because it's moles over moles. And in terms of the value, it should be between 0 and 1, right? It's not going to be a negative value, right? Because it's all about the moles of the gases. Now, remember we said for the partial pressure, if you have an ideal gas, which is typically what we're dealing with, the partial pressure of a gas is always proportional to its mole fraction, okay? So you can write it down as partial pressure of gas I, for example, goes by the mole fraction times by the total moles of the gas, okay? Cool, cool. Okay, so let me show you an example. Let's say we are looking at the partial pressure of nitrogen gas in the air. Okay, so we know that about 78% of the air is nitrogen gas. So that means the mole fraction, right? Remember the concentration or the mole fraction is going to be 0.78, right? And if the total pressure is about 1 atm, which is 101.3 kPa, right? Then the partial pressure of nitrogen gas should be equal to the mole fraction of nitrogen gas times by the total pressure. That will be 0.78 times by the 101.3, and that is going to be about 79.04 kilopascal. Okay, cool. So let's take a look at the practice together on the next page. Okay, so take a look at this practice. You've got a mixture of 6 grams of oxygen gas, 9 grams of methane. We place them in a vessel, in a container, with 15 liter, and the temperature is 0 degrees Celsius. The question is, what is the partial pressure for each gas, and what is the total pressure in the vessel? So if I want to go ahead with all the stuff that are given, it would be the mass for oxygen and methane. I have the volume, I have the temperature, and I know that I always need to convert that to Kelvin, so I just did that, right? I also know that I have R, that's my constant, right? And I am looking for the partial pressure of oxygen, methane, as well as the total pressure, okay? Okay, so take a look at the next slide. So the first step is converting the grams to the moles using the molar mass. Oxygen gas is O2, so that will be 32 grams per mole. That is 6 over 32. And then methane is 16.04 grams per mole, so that will be 9 divided by that, and that is going to give us the moles of both of these gases. The next step is finding the partial pressure, right, for the oxygen using the gas law equation, the ideal gas law equation. So plug in the N, R, and T divided by the volume. It has to be in liter, and that would give me 28.45 kilopascal. Do the same thing for methane, and that is going to be 85.19 kilopascal. Okay. Now, if you're looking for the total pressure, probably the easiest way is summing these two pressures, and that should be equal to our total pressure. Okay. Cool. I hope you like this video. If you like it, give it a thumbs up. There are going to be a couple of more lecture for this chapter. Stay tuned for that. Take care of yourself, and bye-bye for now.